Go away, speak. No, that's what I want. Okay. We're really close. I think we'll probably finish chapter 4 today. That's my goal. We have really just 2 sections left. I'm taking out one of the sections, so I already closed it. It's ready to go. I was in the process of writing the test, but I haven't like published it or finished it yet. All the stuff's there. I just need to like double check it, but I ran out of time because you all are here now. So I'll get that up shortly. My thought is to have it, our test day be on Halloween. So like the time I would have in class. So if you all want to do the test here, cool, do it, leave, go on with your Halloween plans if you have them. If you want to do it at home, that's fine too. My only request is if you're going to do the test here, come at the beginning of the time so then I can go home too. That is my only request. I think that's reasonable. But that way, because I know Halloween is always one of those days where people sometimes go do party things, people do fun, whatever. So that's my way to deal with it. At least it's not the 30th, which is trick or treating night, which I am going to do. I'm excited. I have my other test scheduled in one of my other classes for that night, so I can go trick or treating with I don't get the candy. My child gets the candy. I just steal his candy after. I could fully afford my own candy, but it's more fun to steal his. Okay. So I'll get the test up. I'll probably give you about a week of it open and ready to go. Same deal as last time. I'll look over them after the fact. Other things. Hello, brain, can we turn on? Yeah. Questions or issues about stuff? I think I talked to some people over the weekend with issues here and there. Okay. Are you ready to math? Wow. Usually I get a no. I'm not ready to math. I'm ready to take a nap. All right, we have 2 topics today. We have L'Hopital, which is spelled L Hospital, and antiderivatives, which is doing all of this business backwards. Maybe we don't finish antiderivatives today, but we will definitely finish L'Hopital. What is the date? 22nd. So just to reiterate that in case people want to look at notes. So that's our in-class day for the test. Do your thing. All right. Let me get the theorem of this down. Let's just call it. Oh, I guess it's not technically, there's no S, so, but in my brain, it's always hospital.
That's next Thursday or?
I always give an in-class day if you choose to come and sit here and do your test versus sit at home and do it. Just not that day, no. It's Halloween. Some people like to go party and do fun things, so this is my way to have the best of both worlds. I do boring things, so I'm just gonna go home and probably go to bed. All right. L'Hopital's ruled. So these are dealing with limits. We suppose f and g are differentiable functions on an open interval, I containing some value A with G prime of X not equal to 0 on I. When X is not A. If approaches G of X okay, I'm just gonna finish writing all this up and then I'll kind of walk through. Okay. People are writing, I'll keep you home. Okay, so there's really two versions of this, but I think of it as one version. So we're finding a limit and we have two functions and we have a fraction. So both functions have to be differentiable on our interval and G prime cannot be 0 on that interval. So if the limit of the top function and the limit of the bottom function both go to 0, we can take the derivative of the top, derivative of the bottom, and try the limit again. If those both still go to 0, we can take the second derivative and try it again. So you can chain this because why not? And then eventually you'll get to something hopefully that exists. Note that if our limits go to positive or negative infinity, we can do the same sort of thing. They separate those. I'm not really sure why, but we're going to call it good. So we say as X goes to A, but it can go to A from the left side, A from the right side, positive and negative infinity. It's open. You could do lots of things.
If you say G prime can't be 0, that's derivative on the bottom, the second and end up equal 0. Because if you take the second derivative and it equals 0, is that?
If you take the first derivative and it equals 0, you get a 0 over 0, you could do it again. And if you get a 0 over 0, you do it again. And if this never is non-zero, then it blows up. But if the top eventually, or if they both eventually get to a non-zero, then you're good. I need a drink of water, sorry. All right, do we have the theorem down? It's like people are not writing, so I'm gonna call it good. So let's look at some examples. We have limit X approaches 1 of X cubed plus X squared minus 2X all over X minus 1. So first thing, check. Is it gonna go to 0 over 0? Yeah, it's pretty, you can eyeball that pretty easy. Can we factor it? Maybe. Yeah, we might be able to, but we're not going to, because we're gonna use this rule. So we get a 0 over 0 if I plug in 1. So now, take the derivative of just the top, ignoring the bottom, then take the derivative of the bottom. Do not use product rule here. You're just pretending the top is its own function, the bottom of it is its own function. All right, so derivative of the top, 3x squared plus 2x minus 2 all over 1. Now, if I plug in 1, do I get 0 over 0? Now, if the top is 0, we don't really care. Cool, that's the limit 0. The bottom's really what we're worried about here. So it doesn't. Cool. So now we can plug in our value and we get 3 plus 2 minus 2 equals 3. Ta-da. Done. This is a very lovely rule. Okay. Do we have 0 over 0? Yeah. Before L'Hopital, how would we have dealt with this? Crying. Yeah, we would probably want to cry a little bit, but after we're done crying, then what do we do? ChatGPT, is that what you said? Yeah, I heard you. Okay, assuming we don't want to cheat, we would have had to multiply top and bottom by the conjugate. So we'd say root 9 plus 3x plus 3. So say you're at a test and you can't use all of these things. Crying is always an option, but it doesn't get you too far. But you can't use ChatGPT or what have you. Okay, but we don't have to do that now. We're not going to do that now. Take a derivative. What do we get? I'm just gonna write that off to the side so I don't have to think about it too hard. Alrighty, derivative of the top business is 1/2 times the inside to the negative half times the derivative of the inside, which is 3 all over 1. That looks really weird. Now do we get 0 over 0? No, because we have a 1 on the denominator. I'm going to clean this up one more step. I get 3/2 times 1 over square root 9 plus 3x. And the whole thing's over 1, so I don't even have to write that down anymore. Plug it in. I plug in 0. I get 3/2 times 1 over root 9. Root 9 is 3, so I just get 1/2. Much nicer than the old way. But if I would have showed you this from the start, you never would have learned the old way. Assuming we learned the old way anyway. Okay. Let's look at a couple of other weird ones. Are these okay? Can I move on? No, let's scroll too fast. Okay. Eyeball it, we get 0/0. I mean, you think we're probably going to, but let's check. Let's be official. We do get 0/0. E to the 0 is 1. You get 1 minus 1. Yep. All right. So use L'Hopital. What do you get? What's the top? Yeah, just once. Okay. Beautiful. And the bottom? 2x. Yep, we're going to go through this stage just to see that we get 0/0 again. We get 0/0 again. Okay, so we're going to do the whole process again and see if that helps. So we do it again. We are left with x approaches 0, e to the x over 2. Now do I get 0/0? No, yay! We get, no, go away. 1/2. So sometimes you have to go through and do it more than once, which I already said we could do. There's a bug up there. If that lands on me, I'm gonna scream, just so you're all aware. If that bug gets me, I'm gonna make a scene. I am not tough when it comes to bugs. I will scream like my hair is on fire and run out of
What unit are we in right now?
chapter 4. Oh, did I not put the title on here? Oh, nope, that was me. Or stop. 7, sorry. Okay, before we move on with this one, what is the maximum number of times we will have to do L'Hopital? We definitely will not have to do it more than 4. I think 3 is going to be the max. You're not wrong. Like, we won't have to go more than 4, but I think 3, because we take the third derivative, we don't have anything left. We don't have any variables left on the top. So it's always nice to look at that and say, okay, worst case scenario, 3 or 4 times. Go forth and math. I don't want to math. I've been mathing all day. It's your turn. Are we cheating? I'm teasing. You were the chat GTP comment, so I'm going to tease you about that now. Yeah, yeah. I've been having it write code for me because we've been encouraged to have it like start code for a class and fix it. And a lot of times it just gives me nonsense.
That's what it's supposed to be.
Yeah. It's entirely possible. I just don't understand programming. And so I think it's nonsense, but it's actually decent code. But yeah, that's not my strong area. You get an answer? How many times did you have to take the derivative? Did you get a constant on top eventually? Okay. No worries. Okay. I'm gonna work it on the assumption that this thing is going to zero. Pretty sure it's going to zero. So cool. All right. And more than anything, we care about the denominator. So check the denominator. If it doesn't go to zero, it doesn't matter what happens with the numerator. We're fine. It's when the denominator goes. All right. So we get 3x squared minus 6x all over, okay, 4x cubed minus 12x squared minus 14x minus 12. I think we've decided that the denominator goes to zero again. Yeah, okay. Do it again. Yay. Sorry, I'm full of sarcasm today. I'm tired. Say again? What does our denominator give me at that point? Say again? Yep. You want one too many. Yes. Okay. So as we see, we do not get a zero on the denominator. So we plug in 2, we get negative 14, and on the top, 12 minus 6 is 6. Did you get negative 3/7? No, when you did the third derivative. Okay, then yeah, it does give you the right answer. Like, I didn't think it would give you the right thing, but maybe, weirder things have happened. Okay, makes sense. We good with that? So let's look at a couple infinity over infinity ones, and then we'll do some antiderivatives because I like them more. Oh, I don't want to do that.
Like a default next chapter.
4.9 is technically antiderivatives. So those are fair game on the test. Like I said, I need to double check what the AI bot put on there. I told it 20. I need to double check. I told it to do more chapter 3 than 4. And then it looked either slightly more 3 or even split. But I think I said 10 medium questions, 8 easy and 2 hard. Kind of more or less evenly split or proportionally split. Yeah. So a lot of them will have multiple parts too. So. All righty. So this really becomes helpful when you get infinity over infinity. So you've got some of these, hey, my ex is going off into crazy land. What do I do? Aside from crying. Anybody ever watch Mythbusters? Failure is always an option. No? Okay. That's a great show. If you're bored, watch it. It's funny. They blow a lot of stuff up. A lot of explosions. That's how I got my kid hooked on it for a while. Okay, we've plugged this in. We very clearly see this is infinity over infinity. Like, we don't even have to look real hard. We got stuff going crazy. Any thoughts on what this is gonna shake out to be? Yes, why?
Because the exponent equals are equal on top and bottom, so use the coefficient. I think.
So the old way we would have done this is if we multiply top and bottom by 1 over x cubed, what do we get? So this is interesting because I think that's a quicker way to do this than L'Hopital. Okay, I'm going to multiply top and bottom. 1 over x cubed, and we get 4 minus 6 over x plus 1 over x cubed all over 2 minus 10 over x squared plus 3 over x cubed. That's going to go to 0. That's going to go to 0, 0, 0. 4 over 2, which is 2. So that's a viable option for one like this. L'Hopital is going to take us a little bit longer. But sometimes you see that first, and that ends up being the easier route for you. So I'm not saying there's one right or wrong, just we have options. But we're in the L'Hopital chapter, so let's do our thing. How many times are we going to have to take this derivative? Yep. All right, derivative of the top. Squared minus 12x, and the bottom 6x squared minus 10. Do it again. Go sideways now. Limit as x approaches infinity of 20 for x minus 12 all over 12x. One more time. (24 over 12). We have no more variables in here. Answer is just 2.
Trinity, thinking about how it'll only work if you can give it a every variable. If any of them remain, doesn't that just make it?
Your denominator has a variable on there. It's gonna take the whole thing to 0. It's gonna pull it all over to 0. But if your numerator has a variable, yeah, you have to keep going. And if you get to where your denominator is a constant, but your numerator is not, depending on what your numerator looks like, you might not have an answer. It might just go to infinity. Most of this, like a lot of times, if it's a polynomial on top, that's what's going to happen. But yeah, otherwise you keep going until you're out of stuff. How are we feeling with these problems? Okay. Cool, cool, cool. We did that, we did that. All right. Antiderivatives, yay! So all of this stuff we've learned in chapters 3 and 4, we're gonna do backwards. I warned you it was coming. Yeah.
4.8.
Yes, and I turned the homework off already. So I would rather focus on this. Derivatives, I can spell this word. Antiderivatives. So backwards. I'll give you the formal definition.
These are not integrals.
They relate to them, but they're not yet. We have to practice this and we'll build up some tools before we get to integrals. But honestly, yeah, integral without the sign. A function f is an antiderivative of regular f on an interval I, provided that f prime of x equals little f of x for all x in I. So we start with our little f of x, our standard f of x. And if we take the antiderivative, they use a capital F. And that's kind of standard. I've seen that in a lot of different texts and books. So that is typical. Okay. Okay, so this is called the family of antiderivatives. Let f be any antiderivative I V A T I V E of f on an interval I then all antiderivatives of f on I have the form big F of big C, where C is some constant. So C is some real number constant. That is a whole lot of words to mean that when you take an antiderivative, or when you take a derivative, what happens to our constant? It zeroes out. So when we take an antiderivative, your constant could have been anything. We usually don't have enough data to know what it was. So we add a big C at the end. For example, let's take a regular derivative. Let's keep it simple. X squared plus 4 and big G of x squared plus minus 25. I don't know. Take the derivative of both of these. What do we get? The constant has gone away when we take the derivative. So when we're given just that f prime is 2x and we take the antiderivative, we don't know what the original constant was most of the time. There's some cases where we will. So what we do, if we are given, say we're given little f equals 2x, the antiderivative, we'll talk more about this in a sec, we add 1 to the exponent and divide by that new number. Plus C. The plus C is important-ish. Okay. Find some antiderivatives. Mm, This one, hopefully we can remember, but we haven't done a lot of work with these, so hopefully. This is why knowing your derivatives is so important. So the first one should be pretty straightforward. The second one may take you the sign of t may take you a sec. The one on the bottom, if you remember the derivative of this thing, this is easy. If you don't, that looks like madness. So see if you can come up with it. How long is this section? Yes. Oh my goodness. Okay. Our first one. The derivative of what equals 3x squared?
You.
It's cubed.
C.
What? Let's see. Nice catch. I would have forgotten to. X cubed plus C. Yep. All right. What is the antiderivative of sine? So the derivative of what will give us sine of t? Let's jump. I hate sine and cosine because I always forget which one's which. Because going forward, it's one is positive, going backwards, the other one is. Okay, do we remember what gives us a derivative of 1/1 plus x squared? Yeah.
We'll see. Yes.
Yeah, that is a tangent. So we get big F of x equals tangent x plus c. Nice, plus c. Oh, you're right, it is arctangent, isn't it? Yep. Man. Thanks.
Sine 1 divided by all bottom squared. I just, no.
I don't remember, I always look it up. I'm sorry.
Sine is the same thing, but it's at the bottom.
Yes.
Okay.
Job, thanks.
But. that's a mistake.
See, this is not my area of math, so I never memorize these things. I look them up. I can teach you all graph theory, though. Would you like to learn some of that? It's fun. All right. Let's talk about two rules and then I'll practice these and I'll see where we're. So now we are officially going to do integrals. Look at you. Oh, I guess we should, this is an indefinite integral. So the integral symbol looks like an elongated S with like little loops on top and bottom. And it's indefinite because it doesn't tell us. Our definite integral is going to tell us some things. That was a bug. Indefinite interval will give, or definite will give us some extra information. We don't have that yet. We will get there. That's more of chapter 5, but not yet. So indefinite, when we take the antiderivative, we're gonna get, so we got our x cubed plus c. If we have definite integrals, we do something slightly different. A big important piece, which doesn't feel important, but it is the dx. That tells us what we're taking the antiderivative with respect to. Now, at Calc 1 stage, it feels not important at all. But eventually, you're going to have derivatives, or antiderivatives, or more. And knowing what is first, second, last makes a big difference. And sometimes we can have it so where it's just say y x squared dx. And that means we treat y like a constant in this problem. So the dy dx isn't important now, but it's important that you get in the habit of using it. And sometimes they can throw, like, they'll say dy and they throw an x in there. So you have to attack that a little differently. I got in trouble for not writing the dx because it felt like extra stuff I didn't need, but eventually you will. So just, it's a good habit. Okay, so that is how we write those. That is where I need it to be. And we're gonna have a power rule. Okay, we take our indefinite integral of x to the p, where p is some real number. This could be a whole number, it can be a fraction, a decimal, it can be whatever. Then our antiderivative of this is 1 over 1 plus p x to the 1 plus p plus c. Let's see if we were paying attention. So, yeah. Now to check this, to make sure it follows, look at the thing on the right and take its derivative. Does that give you the thing on the left? Yeah, so we multiply by the exponent, subtract 1. That'll give us what we have. So our rule shouldn't be a big surprise. It flows and makes sense from where we started. We have 2 others. Constant multiple. Oof. And then sum and difference, but we'll get there in a sec. So if we have a constant multiple, that's like saying
You can just take a constant out.
yeah. So just like with our derivatives, where our constant kind of came along for the ride, it's gonna, let's change that letter. It's also just gonna come along for the ride. It almost spelled something unpleasant that I don't want on my board. So M is your constant. I didn't want to use C twice. So, yeah. And you think about it, okay, if we do this the forward way, the constant just came. So if we go backwards, why would that change? So think about it, makes sense. The sum rule, can I fit? I'll scroll back down. And this is also going to be the difference rule. It's the same thing. this works exactly like you want it to work. It's nice when that happens. We separate them out just like we would want to. So at this point, we can deal with any polynomial they give us or anything with crazy exponents too. We can deal with any of that. So we can do a lot of antiderivatives right now. All right, we cool with these? Ready to try? All right, I'm going to give 3 of these. And you get to get creative. I will probably end up needing more space for these, but that's okay. Yeah, I'm just going to squish them together and get more spaces. Okay. If you don't have your derivatives down, practice, 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 practice those. Make a sheet listing, especially like the trig derivatives. I forget those. The the arctangent, whatever. I forget those two. Make a sheet. Find a sheet. They're all over the internet. Make a list. Go spend time in Building 6. The Achievement Center in there will help you drill these in a little bit better. But the only way to get better at them is to practice. As blah as that is, but you do get better at math by doing math. All right, these 3, the first, like all 3 of them need to be rewritten at least a little bit before we can tackle them. The second 2 need a lot more rewriting than the first one. I won't ask who got them, who didn't, because that's not cool, but we'll get there. All right. And one of the worst things about derivatives is depending on what method you use, you can get 2 different antiderivatives and they're both right. It sucks. The best way to check is to take the derivative again. All right, I'm going to scoot all of these dudes down. This used to give me headaches. Sometimes it still does. All right. 3x to the 5th plus 2 minus 5x to the 1/2 dx. I'm going to leave off the parentheses because I just want less stuff. If you want to split this into 3 different antiderivatives, 3 different integrals, do that. I'm not, because I don't want to write that much stuff on the page, but I'm going to treat it like I did. So our first one, we have the constant multiple, and then we have the power rule. So we're always going to add 1 to the exponent. So I get 6 up there and divide by the new number. Clean it up from there. Is that one okay? Okay. The second one, we have a constant. The derivative of what gives us a constant? Yeah. So if we have a constant times x and we take the derivative of that, we're just left with the constant. So this is just going to be 2x. So I mean like meta thinking 2 levels about this. The last one is the worst of this batch. but we still do it the same way. What's 1/2 plus 1? It's 3/2, right? So I get x to the 3/2 divided by that new number, 3/2 plus c. I even forget the plus c sometimes too, more often than I care to admit. The calculus is behind us. Now we just have some cleanup. That's it. That's the problem. Did I lose anyone who's willing to admit it on this one? Or do we have questions on this? What questions do we have? Okay. Second one looks worse, but honestly, it isn't. You know what? You come down here. Okay. Do not be afraid to rewrite these in a method that looks in a way that looks better. We can rewrite this a lot. All right, so 4x to the 19th over x squared minus 5x to the negative 8th over x squared dx. Again, I should have parentheses, but I'm writing less stuff on there. Okay, so I did the opposite of getting a common denominator. Now I can clean up both of these. I have that x squared on the bottom, but I can use my rules of exponents and combine them. So I get 4x to the 17th minus 5x, bring that up, is to the 10th. So I subtract 2 dx. And when you do your antiderivatives, you want all of your x's in the numerators. You don't want anything in the denominator because it's easier to deal with. The first one should be straightforward. So I have 4x, add 1 to my exponent, which is 18 divided by 18. Okay. We have negative 10. Add 1 to the exponent. Negative 9. Watch that. You want to say, okay, add 1 to that. What's 1 more than 10? 11, but it's a negative, so be careful with those. Also known as I got zapped with that a few times. I think we all have. All right, clean up, divide by 2. I get 2/9 x to the 18th, double negative, plus 5/9 x to the negative 9, plus c. I could bring the x to the negative 9 in the denominator, but I'm not. I'm just going to leave it. Questions on that one? The last one, again, looks worse than it is once we algebra or use some algebra on this. So we don't know how to deal with a product of binomials with an antiderivative. Honestly, I don't even know how I would deal with this in any other way than what I'm about to do. FOIL. Get 2z to the 3rd minus 5z squared plus 2z minus 5 dz. Did I add my, okay, I added my plus c. Now we just do the same thing we've been doing, but we do it 4 times. 2 over 4 x to the 4th, that is a 4, not a 9, minus 5 over 3 z, z to the 3rd, plus 2 over 2, that's nice, z squared, minus 5z, plus c. Clean up. And we're done. Okay, I'm gonna not deal with those at the moment. All right, what questions do we have about the first 3 rules of derivatives? Or antiderivatives, wow. Words are hard. Feeling okay with that? Okay. I'm gonna throw a couple weird ones at you and see if you can get there. They like to write it like this. I don't, but just give them a think.
First one, I think I figured out a trick. That's just because I've been doing the derivative of that a whole bunch. Is there a way to figure it out without just already knowing the derivative of the thing?
What is the derivative of
That
that?
is a derivative of natural log. But like I just happened to do that much yesterday, so I can do that. You have to know it.
And eventually we're gonna find that if you have something on the denominator and its derivative is the numerator, it's natural log of the denominator. So yes, you just have to know that, but you'll start to recognize it pops up a lot. It's a useful one. It's why we spent time with those because they're helpful. Even though natural logs are nasty in real world, in calculus, they're nice. Yep. So exactly right. It's natural log. It's basically, do you recognize this from the forward direction? Now we're going backwards. What about the second one? Give it a look. Give it a think. And we can, maybe we don't get there the first step, but we can kind of logic our way through it. So we have e to the x or e to the ax or antiderivative of that. Well, how do we get e to the x with a derivative? The derivative of what is e to the x? Okay. So if we just said our answer was e to the ax plus our constant, why can't it be that? Yeah. So if we were to take the antiderivative of this, we wouldn't get the exact same back. So we have to multiply by 1 over the constant and the exponent. This only works when it's x to the first power. If it's x to any other power, we have to do other trickery, and we're not there yet. It's crazy trickery, madness. But if it's e to the something times x to the first power, take the antiderivative of it. It's a constant. Constants are gentle with us. We can make it work. Okay. I am not going to do the rest of these right now. A lot of this is just the antiderivatives of like trig functions, and I'll get them down later. I'm tired. So I'm going to be here for a few minutes, wrapping paperwork or, my videos and stuff up. If you need me, come chat. If not, I'll see you next time. I'll have the test ready to go by next time.